Hi, I'm Monica, and in this video series, I try to introduce you to topics from the world of data and analytics. In this video, we talk about the topic time series forecasting. Let's go! First, let's define what time series forecasting is. It involves predicting future values based on previously observed data. This technique is widely utilized across various fields, including finance, economics, and environmental science. The importance of accurate forecasting cannot be overstated, as it leads to improved decision-making, better resource allocation, and effective strategic planning. For example, businesses can optimize their inventory levels and manage cash flow more efficiently. Next, we will discuss the key components of time series data. The first component is the trend, which represents the long-term movement in the data, indicating whether there is a general increase or decrease over time. An example of this could be a consistent rise in sales over several years. The second component is seasonality, which refers to regular patterns that repeat over a specific period, such as the increase in retail sales during the holiday season. Lastly, we have cyclic patterns, which are fluctuations that occur at irregular intervals, often influenced by economic conditions like recessions or booms. Moving on to common techniques for forecasting, we have statistical methods such as ARIMA and exponential smoothing, which are effective in capturing trends and seasonality. Additionally, machine learning approaches, including long short-term memory networks and profit, are becoming increasingly popular due to their ability to model complex patterns in large datasets. However, there are challenges in time series forecasting that we must consider. Data quality is crucial. Inaccurate or missing data can significantly impact the accuracy of our forecasts. Additionally, we need to be cautious of overfitting, which occurs when a model is too complex and performs well on training data, but poorly on unseen data. Finally, let's look at some applications of time series forecasting. In the business sector, it is used for sales forecasting, demand planning, and financial market predictions. In healthcare, it can help predict patient admissions and disease outbreaks. In meteorology, it is essential for forecasting temperature, precipitation, and other weather-related variables. Time series analysis plays a vital role in various fields by helping us understand trends and patterns in data over time. This understanding is essential for making informed decisions, whether in finance, economics, or environmental science. One of the key benefits of time series analysis is its ability to forecast future values. By examining historical data, we can create models that predict future outcomes with a reasonable degree of accuracy. This capability is particularly valuable for businesses, as it allows them to forecast sales, stock prices, or product demand, leading to better resource allocation and strategic planning. Additionally, time series analysis enables organizations to evaluate the impact of external factors on data trends. For example, it can help assess how economic shifts or policy changes influence performance metrics. This evaluation is crucial for organizations to adapt their strategies in response to changing conditions, ensuring they remain resilient and competitive in the marketplace. Here, we will discuss the key components of time series data, which are essential for understanding and analyzing trends over time. First, we have the trend. This represents the long-term movement in the data, indicating whether it is generally increasing, decreasing, or remaining stable over time. Trends can span several years or even decades, and recognizing them is crucial for grasping the overall behavior of the data series. Next, we look at seasonality. This refers to regular and predictable patterns that occur at specific intervals, such as daily, monthly, or yearly. A common example is the increase in retail sales during the holiday season, which highlights how seasonal effects can significantly influence forecasting. Then, we have cyclic patterns. These are fluctuations that occur over longer periods and are typically influenced by broader economic or business cycles. Unlike seasonality, cyclic patterns do not have a fixed period, which makes them more challenging to identify and predict. Finally, we consider the irregular components, also known as noise. These are random variations that cannot be attributed to trend, seasonality, or cycles. Irregular components can arise from unforeseen events, such as natural disasters or economic shocks, and it is essential to account for them to ensure accurate forecasting. Understanding these components will help us analyze time series data more effectively and make better predictions based on historical trends. Here we will explore the different types of time series data. First, we have univariate time series. This type consists of observations of a single variable over time. Common examples include daily stock prices, monthly sales figures, or annual temperature records. Univariate time series are often utilized in simple forecasting models, making them a fundamental concept in time series analysis. Next, we move on to multivariate time series. This type includes multiple variables, which allows us to analyze the relationships between them over time. For instance, we can look at economic indicators like GDP, unemployment rates, and inflation rates together. Multivariate time series are particularly useful for understanding complex interactions and can significantly enhance forecasting accuracy. Lastly, we have seasonal time series. These time series exhibit regular patterns or fluctuations at specific intervals, often influenced by seasonal factors. Examples include retail sales that peak during holiday seasons or electricity consumption that varies with temperature changes. Recognizing seasonality is essential for effective forecasting and planning, as it helps us anticipate changes and make informed decisions. Understanding these types of time series data is crucial for effective analysis and forecasting in various fields. Now, we will explore the various applications of time series forecasting across different sectors. First, in financial market analysis, time series forecasting plays a crucial role in predicting stock prices, interest rates, and overall market trends. By analyzing historical data, investors can make more informed decisions, which can potentially lead to increased returns on their investments. Next, we have sales and demand forecasting. Businesses rely on time series models to anticipate future sales and customer demand. This forecasting is essential for effective inventory management, optimizing supply chains, and planning marketing strategies, all of which contribute to improved operational efficiency. Moving on to weather and climate prediction, meteorologists utilize time series forecasting to study weather patterns and predict future climatic conditions. This information is vital for disaster management, agricultural planning, and resource allocation, helping communities prepare for various weather-related challenges. In the realm of healthcare analytics, time series forecasting is instrumental in predicting patient admissions, disease outbreaks, and resource utilization. Accurate forecasts in this field can significantly enhance patient care and optimize hospital operations, ensuring that resources are allocated effectively. Lastly, we have energy consumption forecasting. Utility companies use time series data to predict energy demand, which is essential for grid management. This forecasting helps maintain a balance between supply and demand and supports the integration of renewable energy sources into the grid. In summary, time series forecasting is a powerful tool that finds applications in finance, business, meteorology, healthcare, and energy management, helping organizations make data-driven decisions and improve their operations. In this section, we will discuss the concept of stationarity in time series analysis. First, let's define what we mean by stationarity. A time series is considered stationary if its statistical properties, like mean, variance, and autocorrelation, remain constant over time. This means that the series does not show any trends or seasonal patterns that could interfere with our analysis. Now, why is stationarity important in time series forecasting? For one, many predictive models, such as ARIMA, rely on the assumption that the underlying data-generating process remains unchanged over time. If we work with non-stationary data, we risk producing forecasts that are unreliable and potentially misleading. To address non-stationarity, we can apply various transformation techniques. These may include differencing the data, detrending it, or using logarithmic transformations. It's crucial to identify the right method to achieve stationarity, as this will significantly enhance the effectiveness of our time series analysis and lead to more accurate predictions. To achieve stationarity in your time series data, the first step is to visualize the data. By plotting it, you can identify any trends, seasonality, or irregular patterns that may exist. This initial visualization is crucial, as it helps you understand the underlying structure of the data and prepares you for further analysis. Pay close attention to any consistent patterns over time, as these may indicate non-stationarity. Next, if you observe trends or seasonality in the data, you will need to apply transformations. These transformations are essential for stabilizing the mean and variance of the time series. Common techniques include differencing, where you subtract the previous observation from the current one, logarithmic transformations, or seasonal decomposition. These methods are effective in removing trends and making the data more stationary. Finally, it is important to conduct statistical tests for stationarity. Tests such as the Augmented Dickey-Fuller (ADF) test or the Kwiatkowski-Phillips-Schmidt-Shinn (KPSS) test can formally assess whether your time series is stationary. A p-value below a threshold, typically 0.05, indicates that you can reject the null hypothesis of non-stationarity, confirming that your time series is indeed stationary and suitable for forecasting. First, let's understand autocorrelation. Autocorrelation is a statistical measure that evaluates how a time series is correlated with its own past values. This is essential for identifying patterns and trends over time. When we observe high autocorrelation at certain lagged values, it suggests that past values have a significant impact on future values. This insight is crucial for effective forecasting, as it allows us to leverage historical data to make informed predictions. Next, we will explore partial autocorrelation. Partial autocorrelation measures the correlation between a time series and its lagged values, but with a key difference. It controls for the values of any intervening lags. This means that it helps us isolate the direct relationship between a time series and its past values without the influence of other lags. This is particularly useful when we are determining the appropriate number of lags to include in autoregressive models. By using partial autocorrelation, we can enhance our model selection process and ultimately improve the accuracy of our forecasts. Here, we will discuss time series decomposition, a valuable statistical technique that allows us to break down a time series into its key components: trend, seasonality, and residuals. First, let's define what time series decomposition is and its purpose. By decomposing a time series, we can gain insights into the underlying patterns within the data, which ultimately helps us improve our forecasting accuracy. Now, let's look at the components of a time series. The trend represents the long-term movement in the data, showing us the general direction, whether it's upward or downward, over time. Next, we have seasonality, which refers to the regular, periodic fluctuations that occur at specific intervals, such as daily, monthly, or yearly. Finally, we have residuals, which are the random noise or irregularities in the data that cannot be explained by the trend or seasonality. Understanding these components is crucial, especially when it comes to applications in forecasting. By decomposing a time series, analysts can model each component separately. This method leads to more accurate predictions, as it allows us to account for both the predictable patterns, like trend and seasonality, and the unpredictable variations represented by the residuals. In summary, time series decomposition is a powerful tool that enhances our ability to forecast by providing a clearer picture of the data's behavior over time. First, let's define what the moving average method is and its purpose. The MA method helps us create averages from different subsets of a complete dataset. Its main goal is to smooth out short-term fluctuations in the data, allowing us to better identify longer-term trends and cycles. This makes it easier to spot patterns that might otherwise be obscured by noise in the data. Next, we will look at the different types of moving averages. The first type is the simple moving average, or SMA. This is calculated by taking the arithmetic mean of a fixed number of past observations. For instance, a 5-day SMA averages the values from the last 5 days, providing a straightforward way to observe trends over a short period. The second type is the weighted moving average, or WMA. This method assigns different weights to past observations, placing more emphasis on recent data. This is particularly useful when we believe that more recent data points are more indicative of future trends. Finally, we have the exponential moving average, or EMA. This method is similar to the WMA, but incorporates an exponential decay factor. This allows the average to respond more significantly to recent price changes, making it especially valuable in financial markets for trend analysis. In summary, the moving average method is a versatile tool that can help us analyze data more effectively by smoothing out fluctuations and highlighting important trends. First, let's look at the overview. Exponential smoothing applies decreasing weights to past observations, meaning that more recent data points have a greater influence on the forecast than older ones. This characteristic makes it particularly useful for generating timely and relevant forecasts. Next, we will explore the different types of exponential smoothing. Starting with simple exponential smoothing, this method is ideal for data that does not exhibit trends or seasonality. It uses a single smoothing constant, denoted as A, to adjust the weight of the most recent observation, allowing for a straightforward approach to forecasting. Moving on to Holt's linear trend model, this technique builds on simple exponential smoothing by incorporating linear trends. It utilizes two smoothing constants, one for the level of the data and another for the trend, making it suitable for data sets that show a consistent upward or downward movement. Finally, we have the Holt-Winters seasonal model, which is designed for data that exhibits both trend and seasonality. This model employs three smoothing constants, level, trend, and seasonal components, allowing for a comprehensive approach to forecasting complex data patterns. In terms of applications and benefits, exponential smoothing is widely used across various fields, including finance, inventory management, and demand forecasting. Its simplicity and effectiveness make it a valuable method for generating short-term forecasts. Additionally, its adaptability to different data patterns enhances its versatility in time series analysis. In summary, exponential smoothing is a key technique in forecasting that can be tailored to meet the needs of various data scenarios. Here we must discuss the ARIMA model, which stands for Autoregressive Integrated Moving Average. This is a widely used statistical method for time series forecasting, especially effective when dealing with non-stationary data. Let's break down the components of the ARIMA model. The first part is the autoregressive AR component, which captures the relationship between the current observation and several lagged observations from previous time points. Next, we have the integrated I part, which involves differencing the data to achieve stationarity, a crucial step for accurate forecasting. Finally, the moving average MA component models the relationship between the current observation and the residual errors from a moving average model applied to the lagged observations. When it comes to model selection and evaluation, we need to determine the parameters P, D, and Q. These represent the number of AR terms, the degree of differencing, and the number of MA terms respectively. Techniques such as the autocorrelation function, ACF, and partial autocorrelation function, PACF, plots are used for this purpose. For evaluating the performance of ARIMA models, we often rely on metrics like the Akaike Information Criterion, AIC, and the Bayesian Information Criterion, BIC. These metrics help us select the best model by balancing the goodness of fit with the complexity of the model. Let's talk about seasonal ARIMA, or SARIMA, which is an extension of the ARIMA model designed to handle time series data that exhibits seasonal patterns. First, let's look at an overview of SARIMA. This model incorporates seasonal components, making it particularly useful for datasets where seasonality is a significant factor. The model is defined by a set of parameters, P, D, Q, P, D, Q, S. Here, P represents the number of autoregressive terms, D is the number of non-seasonal differences, and Q indicates the number of lagged forecast errors. The seasonal components are represented by P for seasonal autoregressive terms, D for seasonal differences, Q for seasonal lagged forecast errors, and S, which denotes the length of the seasonal cycle. Next, we will discuss how SARIMA models seasonal patterns. This model is effective in capturing both trends and seasonality, which leads to more accurate forecasting. Seasonal differencing, represented by D, is employed to eliminate seasonal trends, while the seasonal autoregressive and moving average terms, P and Q, help account for seasonal correlations in the data. Finally, let's explore some applications and use cases of SARIMA. This model is widely used across various fields, including finance, retail, and meteorology, where seasonal fluctuations are common. For instance, it can be used to forecast sales during holiday seasons, predict temperature variations throughout the year, and analyze monthly economic indicators. These applications highlight the versatility and importance of ARIMA in time series analysis. Here I will speak about the Holt-Winters method, a powerful forecasting technique that enhances traditional exponential smoothing by incorporating seasonality into time series data. First, let's look at an overview of the Holt-Winters method. This method is particularly useful for datasets that exhibit both trends and seasonal patterns. It does this by utilizing three key components: level, trend, and seasonal factors. Now let's break down these components. The level, denoted as A, represents the smoothed value of the series at the current time, providing a baseline for our forecasts. The trend, V, captures the direction and rate of change in the data over time, allowing us to understand how the data is evolving. Lastly, seasonality, GRI, accounts for the repeating patterns or cycles in the data, which is crucial for adjusting our forecasts to reflect seasonal fluctuations. In terms of applications, the Holt-Winters method is widely used across various industries, including retail, finance, and supply chain management, primarily for demand forecasting. Its ability to predict future values based on historical data, especially when seasonal variations are significant, greatly enhances accuracy in decision-making processes. This makes it an invaluable tool for businesses looking to optimize their operations and planning. Here, we deep dive in the fascinating intersection of machine learning and time series forecasting. First, let's discuss what time series forecasting is. It involves predicting future values based on previously observed data points. This technique is widely utilized across various fields, including finance, economics, and environmental science, where understanding trends over time is crucial. Next, we will look at the role of machine learning techniques in this domain. Algorithms like ARIMA, LSTM, and Profit significantly enhance traditional forecasting methods. They are capable of capturing complex patterns and relationships in the data that simpler linear models might overlook, leading to more accurate predictions. Moving on to data preparation and feature engineering, it's important to note that effective forecasting hinges on careful data pre-processing. This includes addressing missing values and outliers. Additionally, feature engineering plays a vital role. Creating lagged variables and seasonal indicators can greatly improve the performance of our forecasting models. Finally, we will touch on evaluation metrics for forecasting models. Common metrics such as mean absolute error, MAE, root mean squared error, RMSE, and mean absolute percentage error, MAPE, are essential for assessing the accuracy of our predictions. These metrics not only help us evaluate model performance, but also guide us in selecting and tuning the best models for our forecasting needs. In this slide, we will learn the role of neural networks in time series analysis. First, let's discuss the introduction to neural networks in time series. Neural networks are incredibly powerful tools that can model complex patterns found in time series data. Unlike traditional statistical methods, they have the capability to capture nonlinear relationships and interactions, which can often be overlooked. Next, we will look at the different types of neural networks that are particularly effective for time series forecasting. Starting with recurrent neural networks, or RNNs, these networks are specifically designed to handle sequential data. They maintain a memory of previous inputs, which makes them well-suited for tasks that depend on time. Then we have long short-term memory networks, or LSTMs. These are a specialized type of RNN that effectively addresses the vanishing gradient problem, allowing them to learn long-term dependencies in time series data. This is crucial for tasks where past information significantly influences future outcomes. Lastly, we have convolutional neural networks, or CNNs. While they are primarily known for their application in image data, CNNs can also be adapted for time series analysis by treating the data as a one-dimensional image. This adaptation allows them to effectively capture local patterns within the data. Finally, let's discuss the applications and benefits of using neural networks for time series forecasting. They can be applied across various domains, including finance for stock price prediction, healthcare for patient monitoring, and energy for demand forecasting. The ability of neural networks to learn from large datasets and improve their accuracy over time makes them an invaluable asset in the field of time series forecasting. Let me explain. Long short-term memory, or LSTM networks, which are a specialized type of recurrent neural network designed for modeling sequential data. First, let's introduce LSTM networks. They excel in time series forecasting because they can learn long-term dependencies, making them particularly effective for tasks where the order of data points matters. Next, we will look at the key components of LSTM networks. The cell state is crucial as it acts as the memory of the network, carrying information across time steps. This allows the LSTM to retain relevant data over extended periods. Additionally, LSTMs use 3 gates: input, forget, and output, to manage the flow of information. Let me explain. Long short-term memory, or LSTM networks, which are a specialized type of recurrent neural network designed for modeling sequential data. First, let's introduce LSTM networks. They excel in time series forecasting because they can learn long-term dependencies, making them particularly effective for tasks where the order of data points matters. Next, we will look at the key components of LSTM networks. The cell state is crucial as it acts as the memory of the network, carrying information across time steps. This allows the LSTM to retain relevant data over extended periods. Additionally, LSTMs use 3 gates: input, forget, and output, to manage the flow of information. Let us have a look at the profit model developed by Facebook, which is specifically designed for forecasting time series data. One of its key strengths is its ability to handle missing values and outliers, making it a versatile tool for various applications. The profit model employs an additive approach, which means it can effectively incorporate seasonal effects, holidays, and changes in trends into its forecasts. This is particularly useful for businesses that need to account for these factors in their planning. Now, let's look at some of the key features and benefits of the profit model. First, it offers a user-friendly interface, which means that even users with minimal statistical knowledge can easily generate forecasts. This accessibility is a significant advantage for teams that may not have dedicated data scientists. Another important feature is its robustness. The model is capable of handling different types of time series data, making it suitable for a wide range of business applications across various industries. Finally, the profit model includes automatic seasonality detection. This feature allows the model to identify and adjust for seasonal patterns without requiring extensive manual input, which ultimately enhances the accuracy of the forecasts. In summary, the profit model is a powerful tool for anyone looking to improve their forecasting capabilities, regardless of their statistical background. This was our first part on the topic, time series forecasting. We hope you enjoyed the video. Please leave us a like, comment, and of course, subscribe to our channel.